Okay, well, we're very happy to have Takemichi Okui, who's a friend to many of us, a collaborator of mine and former collaborator, and he's going to tell us from Florida State University, he's going to tell us about monopoles. So take it away, Take.
Thank you very much for the invitation, and thank you for interest in my work. So this is my recent work that I did with my former student Vaja Lolatse. Do you see my cursor?
Yeah.
Okay, good. So so he was my student at FSU. Now he's now at postdoc at Oxford, working with Pratik. So personally, I've been working on this problem for many, many years, and finally, I think I solved it. So I would like to share what I found out. So, so let me begin with, since I'm at FSU, I need to talk about Dirac. Actually, both Marcus and John came over to FSU and gave Dirac lectures many years ago. Anyway, so here's a monopole, which I assume is spherically symmetric in this talk and very heavy. So think about monopole and then some electrically charged fermion, which I assume to be massless in this talk. Okay, so thinking about considering this magnetic field produced by monopole as a background, classical background field, we can write down the B field, and then and that B field could come from this A field, vector field. And there are two possible gauge choices. It turns out there is no way to choose a gauge where the vector field is smooth everywhere. So you can choose it to be singular at South Pole or singular at the North Pole. And away from the poles, the difference of the two configurations should be given by gauge transformation, which turns out to be 2g times phi, where phi is the angle from 0 to 2 pi. And so for this, then the corresponding gauge transmission on the fermion, for example, will be given by e to the I charge of the fermion times this gauge transformation, and demanding that this transformation is single valued when phi changes from 0 to 2 pi, that quantize this exponent, and then turns out that the Q times electric charge times magnetic charge has to be half integer. And this is what Dirac found way back in 1931. So actually the 100-year anniversary is coming up quite soon. Okay, so the Q times G is half integer. That's one thing to keep remember. Next, another weird thing that happens with monopole is the behavior of orbital angular momentum. So first, let's think about it classically. So the usual R cross P angular momentum is actually not conserved even around this spherically symmetric configuration. And you can see that quite easily. This R cross Lorentz force, that's a torque. And then just do the algebra, and it turns out it's non-zero. But this also tells us that if I subtract this QGR hat from R cross P, then that combination is conserved. Okay, so this is the combination that is conserved. That's the conserved angular momentum, orbital angular momentum in the monopole background. And quantum mechanically, so that means that the just replacing P by negative I times covariant derivative in the monopole background is not enough. You need to add this minus QGR hat piece, and that and you can check that this works, that the commutation relations works as they are supposed to work. And what's interesting is that when you take the L square of this this angular momentum, it's bounded from below by Q squared G squared. And you can also show that you can saturate this inequality, and then at the absolute value of Q times G, which, as you remember, it's a half integer. Okay, so now orbital angular momentum can be half integer in the monopole background. So now let's combine this with the spin of this vial fermion. Okay, so it's a massless vial fermion, which I take to be left-handed without loss of generality. And so this is the Dirac equation for the vial fermion in the monopole background. And writing this fermion as the radial piece times angular piece as usual, and require. So let's look at the special case where this phi of A, this angular part, corresponds to lowest J, where J is the usual orbital angular momentum plus spin angular momentum. So in this case, as I said, the minimum L was Q times G, and then spin 1/2 fermion, so it subtracts spin 1/2. So that would be the minimum value of J. Okay, so let's require this for phi. Then what happens is quite interesting. So this then the Dirac equation in the monopole background reduces to the simple equation for the radial part. And so this is general equation provided that the only condition I imposed here is that J is at the minimum. Okay, and example of this minimum configuration, minimum J, is the following. So in this talk, I'm gonna mostly consider minimal monopole where the value of Q times G is the smallest, the non-zero smallest value, 1/2. In that case, the minimum J is 1/2 minus 1/2, which is 0. Okay, so the orbital angular momentum is 1/2. Spin angular momentum is also 1/2. So to get total angular momentum 0, you combine them in the usual up-down minus down-up configuration. So the orbital angular momentum and spin angular momentum combined in this way. But as I said, the fact that the chi reduces to the simple differential equation is a general result for any minimum value of J. It doesn't have to be minimal monopole. Now, there are two surprising features here. First one, which is mildly surprising, is that this chi radial part of the wave function satisfies free wave equation in 1 + 1 dimension. Okay, so that means that so usually you would expect when the orbital angular momentum non-zero, you might expect that there should be some centrifugal barrier, so you can't actually get to the origin. But in this case, there's no centrifugal barrier. So actually, this lowest partial wave is able to get to the monopole core without any obstruction. So that's the first surprising feature here. The second one that's really, really interesting, and then the origin of all the interesting questions in this talk, is that this wave, the direction of this free radial wave depends on the sign of Q times G. So if the Q times G is positive, then you only get the ingoing spherical wave, whereas if Q times G is positive, then you only get outgoing wave. So in either case, it looks like you're missing half of the solutions. Okay? That's the I don't have any intuition behind this, but that's what it is. It just comes out from Dirac equation for the lowest partial wave. All right. Now, now let's see what comes out of this interesting reduction in the solutions. So to be concrete, I'm going to take again the negative minimal monopole charge, Q times G equal 1/2, and then I'm going to take -1 magnetic charge, which is seems like a weird choice, but it actually turned out to be convenient for me. So in this case, but there is no real, just a convention. Okay? And so in this case, so consider that to have a pair of incoming wave and outgoing wave, I need a positively charged field and negatively charged field, and consider there are n such a pair of fields, one positive and one negative. And I have, even though this is not strictly speaking necessarily, I'm considering them, I'm sort of imagining these pairs to come from doublets of SU2 in the 12th Polyakov monopole. So just to be concrete, I'm giving them electric charge plus 1/2 for the upper component and negative 1/2 for the lower component. Okay. Then from the previous slide, the upper component has only outgoing waves, and then lower component has only ingoing waves. So plus for outgoing, minus for ingoing, and plus for positive charge, minus for positive charge. Okay. And the sort of standard benchmark example in the literature is SU5 GATT monopole, where you have each generation of standard model fermions give you 4 such doublets. So this guy comes from 5 bar, and then these 3 come from 10. Okay? Anyway, so there's a real example if you like. Well, real example. Now with this, oh yeah, sorry. And then to understand the next slide, you need to understand 2 symmetries in this theory. So there's a U1 electromagnetism which picks up these plus or minus 1/2 charges from the doublet, and since I'm in the limit of turning off all the fermion masses and standard model gauge interactions, coupling and everything, so these n doublets, so I can freely rotate these n doublets among each other. So there's SU n flavor symmetry for these n doublets. Okay? And so there are n-1 diagonal generators for this SU n that are mutually commuting, which I take to be these particular. I'm going to choose these bases for convenience. Okay. Now let's analyze particular some special processes. So imagine first example is n equal 2. Okay, so just 2 doublets. Okay, chi1 and chi2 with plus or minus. And suppose the initial state is, so remember that the ingoing state has to be from the bottom component of doublets. So let's say I take a chi1 minus as initial state. Okay, then the final state has to be made of outgoing states. So let's say it's a linear combination of A chi1 pluses and then B plus B chi2 pluses. Okay. So then I can impose the U1 electric charge conservation. So it's a -1 charge. I'm dropping the overall factor 1/2. So -1 equal A plus B. Okay. And SU2 conservation gives you that. So I'm looking at this one and a -1 generator. So gives you A minus B. So you can solve this. And then you get A equals 0 and B equal -1. So that means initial chi1 minus scattering on monopole gives you, so -1 means it's an anti chi2 plus. So, okay, so chi2 plus bar, that means anti chi2 plus, which conserves U1 and SU2. And then this is a unique solution to this problem. So that means final state is completely fixed. Okay, so this scattering process has to happen at 100% probability. There's no other possible final state. Okay, so this is an example of a process called Kalam-Rubakov process found 42 years ago by Rubakov and Kalam. Okay, another example of.
So do you want to talk about the angular momentum there?
Angular momentum of what?
So this fermion flips its helicity, but the angular momentum is conserved because of the extra.
Well, so they are, so as I said, I'm only looking at the lowest partial wave. So this is J equals 0, this is J equals 0.
Yeah, because of the helicity flip.
Well, I'm taking all the, I'm taking all the fermions to be left-handed chirality.
Yes.
Because I
But
don't
you
want to
have-
get confused
You
by
have chi
helicity
bar,
flip.
so you have chi bar, so you have the opposite helicity in the final state.
Yeah, so if we take say the first two doublets from this example, then this D in example, so D3C would be going to anti D3 here. So in that sense, you can say in the usual standard model left-right notation, you can say it's chirality flip. But I'm taking all the fermions to be left-handed because I don't want to talk about chirality flip. And remember that the spin and angular momentum in this is in this linear combination. Okay, so it's not like as a definite angular momentum.
In the
but
final
total angular
state,
momentum is zero. Sorry?
in the final state, the particles goes off in a fixed direction, right? We detect it.
Well, I'm looking at J equals 0. I'm looking at lowest partial rate. But of course, when you detect it, of course, you will find it at the detector. Yeah.
With the opposite helicity that we emitted it.
Opposite helicity. So it's in this linear combination, right? So up, down, minus, down, up. So
Let's move on.
Yeah. So it's in the superposition of down, up, and up, down. So, but the point is that the J equals 0 is going to J equals 0. So angular momentum is conserved. Okay?
Yes. And if you started with, instead of J equals 0, you could start with just one piece of it with a fixed helicity, and it would 100% of the time go to the opposite helicity.
So when you say,
that's
so are you
an allowed
thinking
initial state too?
Yeah, sort of like a plane wave like initial state?
Yeah, plane waves also scatter. They have an S
so
component.
Then you're gonna
The
have to
final state
decompose
will have the
your
opposite
plane
helicity.
wave. Yeah, you're gonna have to decompose your plane wave into partial waves. And I'm only talking about J equals 0 part of that partial wave.
Yeah, and the J equals 0 component of the plane wave flips helicity. That's what your equation says, or your reaction says.
Yeah, so in the sense that if this was E, then this would be E conjugate bar. Yeah, in that sense, you can say helicity is flipped. Okay, so let's look at n equal 4. So, in this case, you can repeat the same exercise. Okay, then again, the final state is uniquely fixed. But what's interesting, you get 1/2 coefficient is 1/2 for everybody. Okay, and so that's why it's called semitons. If you put all 3 generations of standard model, then you're gonna have an n equal 12. Then this becomes like a 1/6, and 5/6, 5/6, 5/6. So it doesn't have to be semi, but just the point is it's gonna be fractional for any n bigger than 2. Okay, so so this is the Semiton / unitarity problem that I'm gonna talk about. Okay.
So
yeah.
So you're telling, if we agree there's no semitons, then one statement on this page must be wrong.
Yeah, so I'm going to tell you what is wrong in this standard argument.
Why don't you tell us right now which one is going to be wrong so we know what to look for?
Oh, so, okay, so the wrong part would be this part.
So the final state, I can pick my initial state. So you're saying the final state is wrong.
Yeah. So there's no so I'll tell you how this restriction of out only versus in only for the plus and negative charge. How I know how that. So I'm going to tell you that connection is going to be what will be broken, and when you look at it more carefully. Yeah. Okay. So I'm gonna to study this problem. So I'm gonna make some concrete calculations. Okay, and then I'm gonna do calculation in this Polchinski's rotor model. which is which is accurate effective theory in the low energy limit, and then also at the small coupling, small electric charge coupling limit. Okay, and the first step is to so it is true. So despite what I'm going to say later, it is still true that this field is made of only outgoing modes, and then this field is only made of ingoing mode. That is correct. Okay, and so instead of thinking about ingoing that gets reflected outgoing, just put the ingoing wave as a right mover on the negative x-axis, and then put the outgoing fields at the positive x-axis. So all I have is just a massless right mover going from left to right, just continuously. Okay, so that's the first step. So remember that the outside of the monopole core, we solved the Dirac equation. It was free, right? So just free massless right mover here, and then free massless right mover here, and then there's something happens at the monopole core, but the outside of monopole core, all we have is this massless right mover. Okay, so then the next question is what should we do with the core part? And to figure out what should happen at the core, remember that the left, so this part has a negative electric charge, -1/2, and then this side you have a +1/2 electric charge. So the electric charge varies in space like this, okay, and go from -1/2 to +1/2 across the monopole core. And so that means
you just told us that's not what happens. It goes to the antiparticle of chi plus.
No. So I'm talking. So this is the charge of the field. So this field has So for example, chi plus, right? Chi plus will annihilate outgoing particle and create outgoing antiparticle. So these are quantum fields. So it has a annihilation and creation part, but both annihilation and creation operator are multiplied by outgoing mode. And here, here it's only ingoing mode, but has each of them has a particle and antiparticle. So what I'm plotting here is a charge of the field, not the charge of the particle.
That's two different fields, right? It's two different.
Yeah.
Fields.
So this field has charge -1/2. So this chi minus field has a annihilation operator of -1/2 particle and creation operator of +1/2 particle, antiparticle. So the particle and antiparticle have opposite charge. So what I'm referring to is the charge of the field, in the sense that how does it transform under U1 transformation. So here the U1 transformation, say, gives you negative I theta over 2, and here field transform with e to the plus I theta over 2, and in the middle it's some varies in some way. Okay, and
use sign to represent both chi plus and chi minus.
Yeah, so psi. So the psi, if you evaluate psi at the negative x-axis, on the negative axis you get chi minus. If you evaluate psi on the positive x, then it's chi plus.
But
so chi minus is embedded on negative x side.
You're gluing together two unrelated fields.
Yeah, that's right. Yeah.
So this is an arbitrary choice.
Oh, it's not arbitrary in the sense that if you solve so for example, if you solve a Tusk-Polyakov monopole, so if you have a SU2 breaking down to U1 produce a monopole, and if you solve Dirac equation in this background of Tusk-Polyakov monopole, then you see that this is actually this is what happens at the leading order.
You just showed us that what happens is you get chi plus bar as the outgoing.
Well, no. So there's you need to distinguish what happens when you solve a classical wave equation and from what actually happens with everything included, like instant and stuff. So if I just solve Dirac equation in a classical background of monopole, monopole, then what you get is that the when you put the doublet, lower component of doublet in, then the upper component of doublet comes out. And this, of course, this violates charge, right? Electric charge, but this order semi-classical action does not know about charge conservation. So anyway, so I'll get to that point.
You're saying that this is the classical solution that has an incoming wave and an outgoing wave, that it has this form.
Yeah,
but
that's what you're saying.
But this is not this is not a possible quantum theory because it has an.
This is not a possible quantum. This is just when you
as a Whitman anomaly, right?
Yeah. So when you quantize before you quantize your quantum field, you have to find the modes, right, by solving the wave equation. So this is just a relationship between the modes. Okay,
these are two totally unrelated modes, because if you have a Polyakov background, you'd have two doublets. And what you just showed is you go from one doublet to the other doublet.
No. This is what happens within the same doublet if you solve it. So you don't have to worry about Whitman anomaly if you are solving just wave equation. So you just put one doublet, and what happens is that the chi minus becomes chi plus.
I agree. If you do classical calculations, you get nonsense. But if you did a quantum calculation, this is not about actual process. This is just a relationship between modes, right?
Well, he's just finding the classical modes of the theory, and then he's going to quantize it. So let's let him
so the A and A dagger inside of quantum field are multiplied by modes, and I'm just finding out the relationship between those modes.
I have an electron in this part of space, and I'm going to pair it up with a proton in that part of space, and they're just classical modes, and I'm just going to call them one field.
But this is weak solution that has an incoming classical solution that has an incoming free wave and an outgoing free wave.
No, there's a classical solution where it's, I mean, this doesn't conserve charge, so it's not a solution.
No,
there's a
solution. This is a solution.
Charge is
this
conserved.
Is a solution. So I'm gonna we analyze this in the semi-classical expansion. This is what's happening. So the leading term 1 over e squared. This is e to the 0 term, and at e to the 0 term, you just have a fermions moving in the background of classical field, and that term in action does not know about charge conservation, so it's consistent.
So it's a charge violating Hamiltonian.
Right. That's why we need a rotor. Right. So let me move on to the next step. Okay.
Can we go back?
Yeah.
Here.
Yeah.
There's no classical solution that takes you from that incoming state to the outgoing state, because classically there's no connection between them. There's no interaction term that connects them.
No. So when you solve this in the background of Polyakov monopole with the SU2 inside a core, then you can solve this continuously. You just across the core, and then this is what you get. And then sort of this has to be what you get, because we have at this point you have this connection between charge and the direction of the wave, right? So this is only a possibility.
So that's why in the previous slide you found chi plus bar as the outgoing state.
I think you guys are.
No, that's different. That has nothing to do with this. Yeah.
I think Take is saying that this is the classical solution to the theory, and I think you're saying it's not. Okay, or I don't know, but I think let's see what he gets out of this. He's claiming that this is
what I have
just solve the whole
what
theory.
I have is a quantum solution to the problem, okay, which is not directly related to this classical solution of the classical solution between. This is just solving wave equations to find out what modes I have, and then I'm going to quantize in the usual way. So then, okay. So because so I don't have any disorder in maybe I should.
Sorry, can I ask a different question, Tucker?
Yeah.
So, just looking at this though, it looks weird because I'm used to thinking of something like interpreting a solution like this, that I can think about it as, there's some continuous flux of particles coming in from the left, and there's some continuous flux of particles leaving to the right. Okay, but if I try to interpret it that way, it seems that I have to think that the charge of the monopole is building up. Am I thinking about that wrong?
Yeah, so the charge conservation is violated. Yes, in other words, yes, so charge has to build up into the monopole, and that is precisely related to that is related to the need for introducing the rotor. Okay, that's usually the rotor is there precisely for the purpose of charge conservation. Okay, so in fact, if we stop here, then actually semi-classical expansion is not consistent. And then one of the Polchinski's point that for semi-classical expansion to be consistent with U1 charge conservation, you need to introduce rotor. Okay, and then the point is very simple. Yeah.
Can I ask a question a different way? Because I'm just trying to understand. So normally the way I would solve something like this is I would put in a static ansatz, right? Like I would say that all the time dependence is sinusoidal with some fixed frequency, right? And then I would get a spatial equation, and then I would find my solution. But somehow, in that way, I would never find a charge violating solution if I did that, I don't think, in a charge conserving theory. So I guess maybe I have the same puzzle that John has, is that what is the procedure that defines this solution just operationally? Like
operationally,
what do I do?
Operationally, so maybe I should just go a little bit further. Maybe I should have said this first. So just expansion. Semi-classical expansion in E square. So at the leading order, you have a 1 over E square, okay, which is just essentially just gives you monopole mass. And at the next order, you have a quantized, you have a quadratic action for the fermions in the background of monopole, okay, plus quadratic fluctuation for the photon. In this case, at this order, you have just a quadratic theory with no interaction, right? At this order, interaction would be at the higher order, at the order E squared. So here, what we are doing is that we solve a Dirac equation for the fermion in the background of topological of monopole. Okay, then you find what I told you, and even though charge is violated, theory at this order does not know about charge conservation, but that comes at the higher order. So to actually conserve charge, you actually need to put one of the terms that is formally higher order into this lower order, and that's what the rotor is. And that's the only way to make semi-classical expansion consistent. And
it just seems like I'm sorry to keep stopping you back. I mean, even the fermion kinetic term certainly knows about charge conservation, right? I mean,
no, it does not, because gauge fluctuation. So the D slash, the gauge field in D slash here is classical background.
Right.
So when you do gauge transformation, you have to do the gauge transformation on the photon, but that photon is at the higher order.
But what about just the global U1?
Yeah, so that's exactly what I'm talking. So now let's talk about global U1. So this theta, I didn't put the T and X dependence here. So this U1 transmission parameter theta is actually global transformation, okay? But global transformation is actually X dependent because charge changes from -1/2 to +1/2, okay? So even though we have a global theory, we need to do something like gauge field, which is called rotor here, to cancel this position dependent term, right? So formally, this rotor looks like just gauge field, which only depends on time, okay? Because the place where this charge conservation is violated only at the origin. So this rotor sits at the origin and it transforms this way to cancel derivative acting on Q of X, okay? Just like how gauge field works. But this is not a photon field, okay? But mathematically, there's a superficial similarity with the gauge field, so many things work in a similar way. So there's no mass term for the rotor, but there's a kinetic term, with alpha dot square, so on and so forth. So the action of this theory looks like the rotor kinetic term for the rotor, and then right mover, and then there's this rotor times psi that looks like gauge coupling, but it's not, okay? But the way theory is constructed to have a U-bar invariance is very similar and completely analogous to how we construct gauge theory. And as I said, this rotor Fermi interaction is only localized at the core. And now using this from this U1, you can calculate the U1 charge, and then this is the U1 charge of the fermion psi times Q of X. So it's +1/2 for the chi plus, -1/2 for the chi minus, right? And there are n of them, but then the rotor carries charge as well. Okay, so this is how you know this is not a photon, right? Because this guy carries charge.
Go back for a second to the previous slide, just to relook at it for a second. So there's that term where you've marked it as rotor with a little arrow, right? And so if alpha dot were constant, that term would be increasing. So I think in the classical theory, isn't it true that the solution has this wave coming in, this wave coming out, and then the rotor alpha is just increasing linearly with time? Is that what the solution looks like?
So if classically, actually that's not what happened. So this is such classical pictures was analyzed in the Polchinski original paper, and what he showed is that the fermion sort of acts as a friction. So you excite rotor, so you excite a charge on the rotor, but then that charge decays exponentially quickly, and it just dissipates into fermions.
Because of interactions.
Because of this interaction, yeah. And you kind of have to solve this theory exactly because there is no small coupling here. And it's classically you can solve the differential equation basically exactly. It's a simple equation. And then classically pictures that the fermion wave hit the rotor gets excited, but then it decays exponentially quickly, and then just radiate away a bunch of fermions, and those bunch of fermions come with amplitude 1/2 classically, which look like semiton. Anyway, but I don't want to talk too much about classical picture. Okay, so I already talked about this thing, right? So the quantum mechanically, you could interpret this as a dione. So the energy of this rotor, is momentum inertia times omega square. But then if you treat I alpha dot charge as order one thing, and then the energy of the rotor is 1/I, and that energy of the rotor can be interpreted as energy of the dione. But as I was showing here, they're important. You need to have scales, a hierarchy of scales correctly in your mind. And it turns out that so first of all, since I'm doing this very language of talking about fermions moving in the background of monopole, that is a semi-classical expansion, okay? So I have this semi-classical expansion. So E squared is small. So when you look at the monopole, the mass of the monopole, which is 1/E squared R0, and then because E squared is small, that's bigger than 1/R0 monopole core size, and that is even bigger than E squared of R0. That's the diode energy, which I identify as 1/I. Okay, And furthermore, we are also in the usual low energy expansion of effective field theory too. So energy of the fermions, energy of the scattering process has to be small. Okay. So we have this hierarchy of scales. So this is so the theory is valid provided that this hierarchy of scale is respected. Okay? But what's important here is that I cannot just take a limit that the I goes to 0 and then look at the fermion, decouple the rotor, because you're bounded by this inequality. So the finite I is important, at least in the middle of the calculation. You might be able to take I go to 0 limit at the end of the calculation, but not in the middle. Okay. All right. So now I'm going to talk about. I want to describe my solutions to this problem. And first, the executive summary of the solutions follows. For what I call semitonic Kalan-Rupakov process, where the semitons appear, so I already talked about this example, right? So no semitons, and I just get free propagation of chi1 minus going to chi1 minus, despite the fact that the chi1 minus has to be ingoing wave. Okay, I'll talk about how that paradox is resolved. And for the on the other hand, for the Kalan-Rupakov process without involving semitons in the traditional analysis, that conclusion are not modified. So I get the same conclusion as a traditional analysis in a case without semitons. All right. So now let's. As we already discussed. Yeah.
So Taka, sorry to keep making you go back to this, but can I just try one more question? If I go back to your classical solution, okay, just to make sure I'm understanding the back.
I don't know whether
that one. The one you just had. That one. Yeah. Okay. Now suppose I were to calculate the charge flux operator. That's a sensible thing, right? I can just calculate the charge flux. Yes.
Mm-hmm. Yeah.
Right? I calculated on the left and I calculated on the right. So I'm just trying to understand the classical interpretation of this, right?
Do you want to put the rotor classically, or you don't want to put the rotor?
I'm asking it away from the core. So away from the core, far to the left, and I want to know what is the flux of charge.
Right. In that case, you only need
on the right. Classically.
Yeah, you only need this part. Yeah. Right? Because you are away from the right.
So I would not find that it matches. Is that right? Or I do find that it matches?
You would not find they match because the sum of the charges is on the rotor. Right.
Okay. All right.
Yeah. But if you include this first term, everything is conserved.
Okay.
But the energy flux matches, right?
The energy is a tricky thing. So in a regime where actually there's a tension between semi-classical expansion and low energy limit, but semi-classical expansion actually works in high energy limit. Okay, so if you want to strictly adhere to semi-classical expansion, you should imagine that this fermion has a very high energy, so that you do actually excite the diode physically on shell.
So momentum, it comes out with a different momentum. That's the claim.
Momentum conservation can be violated because there's a special translation invariance is violated by the monopole.
Is this the thing that I'm missing? That your solution, that classical solution, is not a stationary solution. Is that a correct statement? It's not stationary.
No, it is stationary.
Well, so for me, a stationary solution means that classically I look for something that has a single frequency.
Yeah.
That would include the frequency for the monopole, not just for the asymptotic. Not just for the asymptotic waves, but also for the whole monopole, the whole system.
Yeah, you can find a stationary solution.
But that's not the solution you're talking about, or it is? It looks to me like it's not a stationary solution. Normally, what I would want to do is to quantize by finding first the stationary solution, right? And those.
Yeah, so stationary solution in principle exists because this is time-independent Hamiltonian, but that's I wasn't we weren't able to solve the problem that way. So we're gonna present different solutions.
That's the thing that I at least was missing. This solution is not a stationary solution.
The what I'm showing in front of you. Yeah, that's not the station. That's right.
It is not a stationary solution.
Right.
So,
but I'm gonna find stationary solution sort of in an indirect way later.
okay.
So let's see.
But then what is it that defines this solution? I mean, once I go outside of stationary solutions, I would guess I have a ton of things. And
so I'm gonna sort of go in directly, and then I'm gonna find, basically, I'm gonna calculate, I'm gonna find exact correlation functions in Heisenberg picture.
So somehow this is a complete set of solutions, so I shouldn't worry about the fact that it's not stationary. Is that right? These are somehow solutions that have simple asymptotic properties, and they're somehow going to be complete. I'm just trying to understand the big picture because these solutions seem weird, right? So how do I think about them?
Which solution? The solution of?
Ones that I keep asking about.
The classical solution?
Yeah, those classical solutions.
This classical solution, so you find this classical solution in a non-stationary way, in the sense that
but it says that psi is a free massless right-moving fermion.
I mean, I think somehow you've imposed boundary conditions at infinity, that this is incoming and outgoing.
Well, that's not boundary conditions, because if I solve this equation of motion locally here, I only find ingoing solutions.
Okay.
Yeah, those are the only solutions I have here. So
you would say there are no stationary solutions somehow. So you're forced to use these solutions.
But he's going to find quantum solutions that have stationary limits.
So it must be stationary. So I think the reason you're saying it's stationary is because you would think the charge will be building up continuously on the monopole, but that's not what the solution is. Because the dion rotor almost immediately discharges the charge. It's basically charge coming in from left side of the rotor and charge coming out of the right side of the core is basically the same. Because as soon as charge build up, it immediately discharges in the limit that I is small. The I meaning this I.
Okay. Let me go on.
Yeah.
I don't want to stop you.
So, okay. Yeah, so what is wrong in, so traditionally you would say that is impossible because I don't have outgoing solutions for chi-minus, right? So free propagation is not even possible. It scattering has to happen. But so basically what was missing is that so what was wrong is the presumption that I have to use to create outgoing states, I have to use chi plus, and that's simply not true. So I'm gonna show you. I'm gonna show you a different operator that can create outgoing chi minus state. Okay, so if I use chi minus alone, of course that creates ingoing state. Chi plus alone will create outgoing states, but that has a wrong charge, right? But I can combine the rotor and chi minus to have a correct charge, okay? And which you can see pretty easily. So chi minus has negative charge, chi plus has positive charge, but the rotor, shifts this way under U1. So if I multiply e to the alpha, this whole thing has a charge of chi minus, okay? Even though it contains chi plus. So then the question is it possible for this operator to interpolate outgoing chi minus particle? The answer is no for generic choice of time here for the rotor. But the answer would be yes if this tau is equal to t minus r. In other words, when you put this e to the I alpha on the light cone of chi plus, then this whole operator can create outgoing chi minus state. Okay. And I'm going to show that by direct calculation. And so Polchinski already calculated Green's functions involving fermions only. So this is a formula. Okay. So I have n psi's, n prime psi daggers at various positions and various flavors. And that is a so the exact answer to that correlator is that Z times W naught, where W naught is the free Green's function. Okay, so you just pretend your theory is completely free, literally free, and then write down the sum of product of free propagators that you would like write down for free theory. Okay, but then it's multiplied by Z, which is the important part, and it's basically a Gaussian integral. Okay, and with some coefficient A and B, where A and B are made of so A only contains a positive X. A is turned on only for positive X. B is turned on only for negative X. Okay, and A only contains positive frequency. B only contains negative frequency, and so on and so forth. Okay. Now, so this is Polchinski's result. And then, for example, let's just look at the simple 2-point function case, right? One psi and one psi dagger. In that case, the W naught is just simple, just single propagator. So this is the propagator of massless right mover in position space. And this A and B each have just one term each for psi and psi dagger. Okay, so this is Polchinski's result, and then this there's a IR cutoff, which I'm going to talk about later, and UV cutoff, which is just given by the ion mass, if you wish. Okay. Now, let's now insert the e to the alpha to this thing. Okay, so I just took the Polchinski's formula and I inserted the rotor and redo the Gaussian integral. Okay, that's all I'm doing. Nothing is fancy here. Okay, so I'm inserting this e to the alpha times theta of x that I told you about. Okay, so that modified this A and B coefficient to A tilde B tilde by basically adding these things to the exponent, right? So then the mu Z is contains A tilde times B tilde. Okay. So now you observe it. So this generically, for generic choice of tau and tau prime, this is some non-zero thing. But if tau is equal to tau minus t minus x, and tau prime is equal to t prime minus x prime, A vanishes, right? So that makes this Z equal to 1. So that means this correlator is exactly equal to free propagator. Yeah.
Sorry, these thetas are just step functions?
Yeah, sorry, I forgot to say. Yeah, theta is a step function.
Yeah, they're okay.
Yeah.
Good. Okay, just want to make sure.
And it is not a step function if the core size is non-zero, but okay. So this is basically we exactly shown that when the tau is equal to t minus x, the Z is equal to 1, and this correlation 2-point function is exactly equal to free propagator. And so that's what it is. Okay. And so what does this mean? So we have so these are exact Heisenberg operators. Okay, so there's exact correlation function, which becomes free massless propagator. Okay, and this operator, this composite operator, is simply chi minus itself if x is on the negative side, or if we are looking at incoming part of the ingoing part of the section, or if x is positive on the right side of the core, it's this combination that I talked about. So this still has a negative charge, negative 1/2. Okay? So basically, this means that we solved for the one particle spectrum exactly in this theory. Okay. So so this is in a position space, but if I go to momentum space, that momentum eigenstate is the exact energy eigenstate of the full Hamiltonian, which is a stationary state by definition. Okay, and this the chi minus creates chi minus by definition, and then the state freely propagate and then gets annihilated by this chi plus eta alpha. So so that this shows that chi plus eta alpha annihilates chi minus, okay? Or the dagger of that creates outgoing chi minus. And that's and nothing else happens because this is a free propagator.
The state has a negative charge, but if you measured where the charge is locally, isn't part of the charge still sitting on the monopole?
No, so I can give you two answers for that. So one answer is that as I said, classically, so you give a +1 charge, so sorry, -1 charge temporarily to the rotor, but that immediately discharges. So classical picture would be chi minus hits the core and it become chi plus, and then rotor instantaneously acquires a -1 charge, but this -1 charge immediately discharges. It just goes with the chi plus fermion. I think that would be the classical picture. So at the end of the day, what you see, the outgoing state, that it has a -1/2 charge. But I don't like that picture because it's classical. Quantum mechanically, this dione excitation is just a virtual state that only leaves delta t on the order of I from a certain principle. Okay, so the charge is charge doesn't stay there as a.
But when I
this -1 charge is not on shell, so to speak.
If I do a global rotation at some time, alpha only has support at the monopole. Doesn't that tell me that that part of the transformation is because there's charge at the monopole?
Global, but it's only but it's at t minus r.
Yeah, so sorry, the operator.
Yes,
sorry. Hey, this is localized at the monopole at the time of scattering.
Yes.
At the time of scattering, of course, it's on the right shell.
At the time of scattering, yes.
Yeah, because alpha at the time t minus r. So that's.
So are you asking some question?
No. I'm just saying that.
Oh, yeah, just clarifying for me.
Yeah, it's just right.
Okay.
I mean, it's alpha is a time-dependent Heisenberg operator. Alpha at t is the origin at time t. So alpha at t minus r is the origin at the time of the scattering. Then, of course, the support is on like cone of that.
Yeah,
so it goes with the outgoing
calculation shows that if you are away from that origin, then you don't get this result. It's really crucial that the rotor sits at the tip of the light cone of outgoing chi plus.
Just make a suggestion. So, we're about at 1 hour, and I think we really want to hear you finish. But I just want to suggest that let's pretty much let Take tell the rest of his story, and then those of us who are interested in grilling him further, can you stick around for a little bit, Take, or do you have to go?
I can stay maybe 20-30 minutes. Yeah, that's not a problem for me.
Great. Okay.
Eventually, I need to take Kai to robotics. But, yeah.
Well, okay, yeah, but as long
let's
go. Let you finish your story, because I think we've slowed you down a lot, and so let's let you tell the rest of your story.
But this is great. This is exactly what I wanted, because
come back. Okay.
No, I really need this thing, especially for Zoom talk, because when you give Zoom talk and you don't hear anything from the audience, that's terrible, right? So this is actually great.
We don't have that problem now, so.
Yeah.
So go ahead.
Okay. Yeah. So for me, this is convincing that the chi plus eta alpha at T minus R, I mean, dagger of that creates outgoing chi minus because it just gives you free propagator. And since free propagator saturate the unitarity, I mean, right? So this happened at 100% probability. Okay? There's no other possibility. Okay. Now, yeah. So that I'm just summarizing. So this is just a summary of what I told you. Okay, just a free propagation, no semitons, no scattering. Okay, and what we found here is that so naively we looks like we lost half of the states because for example, chi minus only have ingoing, chi plus only have outgoing. So look what happened to the other half. The answer is that the other half of the states we seem to have lost is actually interpolated by this composite operator. Okay, so at the end of the day, we have a full spectrum of both ingoing and outgoing modes for every fermion, regardless of the sign of this Q times G, despite what we found classically, semi-classically. Okay, so that's the biggest thing. So we do have a full spectrum of ingoing and outgoing. Okay, and this is something that they probably everybody is wondering. That so what is this e to the I alpha thing? So I found it in 1+1 dimensional description. What is it in full 3D description? And that's a future project that I'm eager to work on. And and my hunch is that it's related to this fractional vortices thing that we discussed in a paper by Chaba and John and a few other people. But I don't know. That's just my hunch. I have not. I don't have any concrete relation to report yet. So, anyway, so let's so that was about semitonic case. So let's now talk about the other second part of the talk where let's talk about the Kalman-Rubakov processes without involving semitons, even a traditional analysis. Okay, so I talked about these two examples before. Okay, so let's talk about the first one because that's simpler than the second one, but the solution is basically the same. Okay, now the problem here is that so this is a case where traditionally we didn't have any problem with chi1 minus become chi2 anti-chi2 plus 100%, no semitons, no problem. But then now I say that it's a free propagation. Chi minus become chi minus, 100%. Okay, so you can have two different free propagations. So what's going on? Now I seem to have a unitarity problem, right? And same thing for the traditional, so the n equal 4 case. Okay. Now the solution is the following. Okay. So basically, these two seemingly different final states must be actually the same final state, and that's exactly what I'm going to show. Okay. To do that, so I'm going to calculate this 4-point function, two psi and two psi daggers at the 4 different places, and then 1 and 3 have this rotor e to the alpha in it, but the 2 and 4 doesn't have rotors with it. Okay, so this is not a typo. What you see is what I meant. Okay, and so then you calculate this using the formula I told you, and you get the W naught, which is a free propagator part. So this is a bracket is a free propagator. Okay, and this S12 is the T1. It's basically T minus X, okay, between the 2 points. And so this is the free propagator part. And then the interesting part is this Z, okay, which turns out if you just do the calculation, do the Gaussian integral, you get this result, okay? Now what's happening, so what I'm interested in is the following. So this is the composite operator that gives you, gives you chi1 to chi1 free propagation. And then this psi2 is what gonna give you the traditional Kalman-Rubakov process, final state. And I want to show that this composite times psi actually gives you free propagator, so that they create an analyte same states. Okay, and then I and I can show that by looking at the following special limit of this correlation function. So imagine that the 1, 2, points 1, 2, and 0.34 form separate clusters. Okay, so 1, 2. So basically, I'm gonna have a large separation between the two clusters. Okay, and if you do that, the left-hand side, this must be factorized into the product of two correlation functions, just cluster decomposition. Okay, and the right-hand side, you take the limit that this separation gets large, and then you and then this right-hand side z times w naught becomes this. Okay, so I'm going to skip the algebra. Okay, so you see that so you can identify that this 1, 2 cluster is this 1, 2 part, and then a 3, 4 cluster with a 3, 4 part, and so you get this result. Okay, and because of this multiply and complex conjugation, you can put this arbitrarily phased e to theta, which cannot be determined by this process. And I don't have time to go into the detail here, but this parameterizes. So there's a degenerate vacua like theta vacua in QCD, and this theta parameter is degenerate vacua. So Polchinski paper has a very nice discussion on this part, but that's not particularly important for me, so I'm gonna skip. Okay, the point here is that this is proportional to free propagate, okay, up to a phase. So that means if I is 1 and j is 2, then chi1 minus e to the I alpha creates the same outgoing particle as chi2 plus, okay, which by definition is chi2. Anti-chi2, right? Therefore, there's no unitarity problem because the two seemingly different final states are actually the same, one and the same final state. So no unitarity problem. And the identity of this final state particle is given by chi2, okay? Namely the same as traditional Kagan-Rubakov result, okay?
But don't they have opposite helicity?
Opposite helicity. So I don't quite understand what you mean by helicity. I mean, they carry the same gauge
spin
charges.
dotted into momentum, I mean.
Spin dotted into, yeah, I know
One is a left-handed field, one is a conjugate of a left-handed field, so that means opposite.
I made all my fermions left-handed.
Yeah,
so
and
yeah,
the conjugate
so
makes
this
it
the only
right-handed.
thing. So both E and E conjugates are left-handed fields. The only thing that's different is charge, right? Okay, but they have the same charge. They have the states created by chi1 minus e to the alpha dagger and chi2 plus have this exactly same gauge
dagger
charges.
changes left to right, so you change the charge, you change the helicity. So you make them have the same charge, they have the opposite helicity.
No. With dagger, they have the same charge. So chi1 e to alpha, chi1 minus e to alpha dagger has the same charge as chi2. So let's see. Let me read what I wrote. So the state created by this chi1 minus e to alpha dagger, that state has the same charge as the state created by chi2 plus, which is chi2 plus bar. They have the same charge. So
bar has the same charge as not bar? I don't know.
Yeah, because I have e to the alpha, which flips the charge. Right. So
and bar
plus
has
and minus.
Bar has the same helicity as not bar?
So bar just means antiparticle.
These are very detailed
this is a species, particle species. I'm not talking about
tell the rest
here.
of the story, and let's save these very detailed questions until the end. Okay. All right. Let's try to get the big picture. How much time do you think you have left?
I think I'm close to be done. I have one more important point to make, but then that's it.
Yeah, let's let him make the point, and then we can come back to all of these things.
So,
and then people who are not as interested can
right. So no unitarity problem, they are the same state. But then if you have been following the formula closely, then you will say, wait, right? Doesn't our formula say this correlate is 0? Because remember that the way you calculate this is that you put the free propagator here for W naught. And of course, free propagator between psi and psi is 0, right? Okay, so what's going on here? And that's where this subtlety with the IR cutoff comes in, which is related to the anomaly of this theory. Okay, so there's one anomalous U1 here, which is the overall common rotation of the all fermions by the same phase. Okay, so that counts the total number of fermions in the theory in the process, and that is anomalous under the presence of rotor. Very much similar to how gauge anomaly arises. Okay, and so that gives you anomalous conservation law for the total number of fermions. Okay, and the point is that in my formula, which is also Polchinski's formula, we impose the sharp IR cutoff here, which removes low frequency modes from the theory. So then that such removal does not allow the initial and the final value of alpha to be different, because you are restricted to periodic modes. Okay, and that is not compatible with this thing, right? So if the number of particle, if number of psi and number of psi daggers are different inside your correlator, that corresponds to non-zero delta alpha, which is not compatible with the IR cutoff that what he imposed. So our method, our formula is not valid when you have different number of psi daggers. So not valid for this thing. So actually we don't get this conclusion. So there's no contradiction. And for this 4-point function I told you about, okay, that has an equal number of psi daggers. So that calculation was correct. So there's no problem, it's perfect. Everything seems consistent with each other, okay? So that's it. So this is a summary that I already said those things. So let me skip to one last slide, which just who cares, right? So that I'm saying that when you look at the bounds on the monopole flux as a function of monopole velocity, the strongest bounds, this is a plot I stole from Super K paper from 2012. And all these strongest bounds, of course, Super K is the strongest, right? And then that comes from Kalan-Rubakov process. All of these come from Kalan-Rubakov processes, sometimes from the sun, sometimes from the neutron star. And they rely on this fact that whether it's a semitonic or non-semitonic, okay, the Bayer number and lepton numbers are violated. So whatever semitons are, we don't know what semitons are, but the Bayer number is violated by 100% because of Kalan-Rubakov. Okay, so the cross section of monopole hitting, say, proton, and then get the proton decay. That cross section given by the geometrical cross section of the fermion, which is really strong. That's how they get these really strong bounds. But now I say that option number 2 is wrong. The option number 2 should be just free propagation. Okay, but to do the real fermiology, I need to put the fermion masses back in. Also need, of course, the fermions quarks are confined inside nucleons, and then I don't understand what free propagation would mean inside a confinement. So I need to work out those things. Okay, but so that those are the future project. But for the fermion masses, I think I know what to do, because Polchinski actually already calculated purely fermionic correlators for massive fermions. So I think I just need to stick in my e to the alpha to his massive formula. Okay, maybe I cannot do any integral analytically, but I can study numerically. Okay, so then so this is an advantage of this rotor approach compared to a boundary conformal field theory approach by David Chon and Van Beest and those people. Okay, for confinement, it's more challenging, obviously, but I have some ideas that I want to try out. So So the phenomenology is to come. All right, thank you very much.
So here's what I propose. I propose that we first have questions by people who are not me or John, and then we will clap again, and then, you know, we can see if Take is willing to answer yet more questions by me and John. So any other questions?
So when you start off by saying if you have like n equals 4 flavors, you say that this kind of scattering would produce semitons. Why would you not stop there and say, oh, n equals 4 just must not make sense? Why would you pursue that theory further and expect it to make sense if it seems to give you these things that violate rules about Hilbert space?
You mean that so your viewpoint is that n equal 4 flavor theory is simply inconsistent, like anomalous case theory?
Right. Why not come to that conclusion instead of pursuing of like,
well, because, for example, like let's say take issue 5 gut monopole. I mean, this theory is certainly in the UV above gut scale. This theory certainly makes sense, right? Just have issue 5 gut with one generation of standard, one generation of 5 bar and 10. That theory I don't see anything wrong with that theory. Okay, and this theory does produce monopole upon symmetry breaking. So to me, it is reasonable to expect that there should be some sensible low energy phenomenology in this case. And I think there is a lot sense. Now my answer is yes. There is a sensible phenomenology.
Without the existence of monopoles in a Lorentz invariant theory, and then monopoles were discovered in Lorentz invariant theory. So,
So moral of the story: don't
So-
be too quick to rule things out.
yeah, I mean, it's subtle,
unique
so
thing
it's
that
very
makes sense.
subtle, but yeah, it seems like this theory has to make sense as far as we understand. This theory
Okay.
totally makes sense.
Yeah.
Well, 2 is actually free propagation. So what exactly is the final state then?
N equal 2 case?
Yeah, whatever in your second line, right? The one you write down is semiton case, which doesn't make sense. You say it's a free propagation.
Yeah. So for example,
What
the
exactly
option
is
number
the
2,
final
correct option number 2 is U plus M become U plus M. That's
The
it.
same U or a different U?
Same U. So if you attach the other
Or it
quantum
was
numbers like
I1
issue
and
3,
I2.
We're
they
not
have
allowed
the
to-
exact same gauge quantum
Right.
number, so they're exactly the same states. So like for example, E does not become E conjugate bar. I'm saying E becomes E.
Did you have a?
So no helicity flip in your language.
I think Shingy, a question?
Yeah, so you might have said this already, but in the beginning you get this in and out by doing Dirac equation, but then you add the rotor and solve it. So does the rotor modify the Dirac equation itself?
Yes. I mean, say if you start from this action, yeah, if you derive the equation motion from this new action with the rotor, of course, now the Fermi equation motion does have a rotor in it. Yeah, so that's it modifies.
Okay.
Yeah. So what Polchinski did in the first half of his paper, that he solved the classical equation motion and reproduced the Semiton puzzle. So if you just look at the like Marcus was saying, if you calculate the flux density of outgoing states, it's 1/2. Flux density of the fermion number current, not the electric charge. So he reproduced the Semiton puzzle. Classical.
You say this is the case when you have to prove a political monopole, you just solve the how do you get this one? Does
Could
the
you repeat the
rotor
question
come
again?
out directly, or is something Polchinski putting by hand?
Could you repeat the question again? Sorry.
Was the rotor put in by hand, or did it come out somehow from the exact solution? From Polchinski?
I didn't read.
Well, so in Polchinski's rotor paper, he introduced rotor in pretty much the way I introduced, that basically from some combination of U1 conservation plus some power counting in a semi-classical expansion. But since this rotor physically corresponds to dione excitation, if you look at the full proof Polyakov solution, then yeah, the rotor would correspond to some internal rotation in the SU2 space, like some configuration of XY gauge bosons inside a
It's a
core.
gauge parameter from SU2. It's a leftover gauge parameter from SU2.
Yeah, the charge part.
I hope I allowed to ask one thing.
Yeah,
Sure,
you're not me.
of course.
Go ahead.
Okay, thanks. Yeah, thank you, by the way, Davis Fox, to accommodate me. And so one question I probably don't understand, you probably told, but it's a basic point, is that in the case that the final state involves semiton, you said that by dressing this rotor appropriately, you can interpret all the branches of the final state semiton as the same particle as the initial state. Fine, you just address it to I alpha or something, which is an operator on the light cone of the scattering position in space-time. And so why, in the case of Karam-Rubakov thing, which was not the semiton, why you couldn't do the same thing and say that nothing happened? That's probably what you said as
well. So so
you don't have to, but why you cannot do it?
So we're talking about
what's the difference? Yeah, and then the next stage.
So N equal, right? So this
question. Yes, this question.
Right.
Yeah,
so,
I didn't get that part. Sorry.
So the calculation still goes through. So chi1 minus does become chi1 minus.
Yeah.
Okay. But then traditional analysis also say chi1 minus become chi2 plus bar. Okay.
Yeah.
And of course, chi1 minus and chi2 plus bar, they have the exactly same charge. Okay. And
but usually different low energy particle in the SU5 GOT.
Right. So if you look at so they cannot be distinguished by non-anomalous symmetry. The only symmetry that can distinguish them is the anomalous symmetry that I mentioned a little bit. Okay. So another way to reach the same conclusion, to calculate the fact that this thing dagger that correlator is a free probability that they are the same state. Okay, but then is it the same as chi2 plus bar, or is it the same as chi1 minus? Right, and you can identify which one it is by looking at anomalous charge, which is allowed to do as long as you're away from the rotor, because anomaly is localized on the rotor. So if you do that, it turns out this state, this one and the same state, has identity of chi2 plus bar.
So what's anomalous symmetry in SU5?
Oh, so the anomalous symmetry is this one. Where did I? Yeah, this one. Just the total fermion number. The global rotation of all fermions by the same angle. And that is anomalous in the presence of rotor. But if you look at the integrand, of course, this is localized at the core because Q prime X is basically a delta function at the core. So if you're away from the rotor, you're allowed to use this anomalous symmetry to say label the states. And then what turns out is that this particle, this final state
Yes. Okay,
is
Kara-Rubakov process is Kara-Rubakov.
Kara-Rubakov. Yeah.
Okay, so you have to check that. And
Yes,
you
we
can
checked it. Yeah, we checked it. But I think,
and then
I think
unambiguous.
but I think, to me, this argument is almost convincing in a sense that this free correlator, exact free correlator, tells us that they are the same particle, right? So we don't know what this chi1 minus eta alpha creates, except that it's the same particle as chi2 plus creates. Okay? And then by definition, chi2 plus creates, chi2 bar. Right? So to me, that is almost this is almost by definition kind of argument that's almost convincing. But we check the charge just to be.
Yeah, because otherwise, Semiton case and this case is right. I mean, in this case also, you could say nothing happened.
Right. In a Semiton case.
Yeah, Semiton case, you just dress appropriately. It's the same as the initial state. And why not the same thing?
But in a Semiton case, in the n equal 4 case, if you start from one particle initial state, then there's only one option. Okay, so if you don't have two options, we only have one option. That's the same particle. Yeah. But the same thing happens if you have two particle initial state for n equal 4. Then you have this same kind of ambiguity. Okay?
Ambiguity, right? So you need to check that.
So is it chi1 minus plus chi2 minus or chi3 plus chi4?
Yeah. Okay.
Yeah. And then
thank you.
By the same argument, you can identify them to be
so
that is the correct one.
I suggest we thank Take. We're a bit over time, and if he has some time to stick around, and people who are not me and John, and also not Yasunori, not Yasunori. let's thank Take for a very stimulating and thought-provoking talk.
Thank you very much.
Okay, thank you again, people. Marcus, thank you. Bye.
Yeah, good to well.